introduce myself. Probably you know, my name is Muhammad Azam, and I'm currently working with Carnegie Mellon University as a senior research scientist, and I'm currently at their Qatar campus. So my area of work is mainly cloud computing and Internet of Things, and I work on a middleware technology that is related to both cloud computing and Internet of Things. It is known as fog computing and edge computing. So we work mainly on resource management, on fog computing related to IoT, and resource balancing, power sharing, and offloading related challenges that are associated with different domains that are linked to Internet of Things in one way or the other. For example, intelligent transportation system, or smart healthcare, smart cities, smart waste management, things like that. So in this particular presentation or talk, we're going to talk about the role of fog computing for industrial Internet of Things and Industry 4.0, as you can see the title of this slide. So this is the outline of this presentation. We are going to go over the background of all this stuff. What is industrial IoT? What is the role of fog computing? Why do we need that? Why fog is necessary in this regard? And the key components of industrial IoT. We're also going to learn that with fog computing, what is the future of industrial IoT? What does fog do to industrial IoT? And for those of you who are interested in industry-related research, for example, anyone working on industry-related PhD thesis or something like that, I think the last section would be really important for you. The recent challenges, because you can go over some of the key challenges and also the potential solutions to those challenges. So let's go over the background of all this stuff. So I think by now you know what is cloud computing. Cloud computing is not what we are seeing right now on the screen, right? So cloud is actually a set of resources. Cloud will provide us resources such as computation, memory, storage space, data, and applications. And all these resources are available through set of servers that is known as data center. Okay? And these resources are accessible over the internet. So these are the main attributes of cloud computing. We have resources, the resources that I have mentioned. They are available over the internet. What's the key benefit of cloud computing? The main benefit is that you don't have to purchase those resources. Rather, you will use those resources and you will pay the rent for those resources. So that's the benefit. I, as a cloud user, I don't have to buy those resources. I don't have to worry about the maintenance of those resources. I just pay for the rent or pay for the use of those resources. And this is how cloud computing goes. This is the one corner of what we are going to discuss in this presentation. The other corner is the Internet of Things. So we have two, and the other is Internet of Things, or IoT for short. So Internet of Things refers to when anything can be connected to the internet. Anything. It can be intelligent device. It can be a sensor. It can be a machine. It can be a living being. It can be a dumb object, for example, a tree, or a vehicle, or your student ID, your access card, your office card, whatever it is. So this is the concept of IoT. But then why do we connect these things? Why do we connect these intelligent and dumb things? Because we receive data from those things, and based on that data, we create applications, we create services. This is the key concept of Internet of Things. There are different variants of Internet of Things. For example, when we talk about Internet of Things plus people, when we include the people in Internet of Things, this is known as Internet of Everything. The other variant is Internet of People. This means that when we are talking about only the people, for example, those services that deal with crowd sensing or crowdsourcing, they are related to Internet of People. The other variant of Internet of Things is social Internet of Things. In this case, we have applications that socially connect to each other and create a social Internet of Things. Then we have Internet of Me. When I take my own self online, my brain is online. This is known as Internet of Me. For example, based on my mood, different actions would be performed. For example, in a smart home, the lights would be turned on and off, or the color of light would be decided, the music would be turned off, different actions would be performed. So this is Internet of Things. When we strictly talk about the industrial things in an Internet of Things, then this is known as industrial IoT. So in industrial IoT, we are not generally talking about the things. Those things are industrial things. That's the difference between IoT and industrial IoT. Then we have Internet of Drones. In this case, we have multiple drones that are accessible over the internet and controllable as well. So this is for different services. For example, for smart agriculture, we have multiple drones that are spraying on the field or things like that. So this is IoT. We generalize Internet of Things as IOX. So IOX means IoT or IoE, IoP, etc. So these are the two corners of this presentation or this discussion. One corner is cloud computing and the other corner is Internet of Things or IoT. So we know both of these things by now. What is industry? Since this presentation is related to industrial IoT, we're going to learn what is industry and what is the role of industry in case of IoT, the scope of industry. Industry means production of goods and services. So these are the two things. Either you're producing a good or you're giving a service. If that's the case, then this is industry. Industry has generally three categories. Number one is primary. Primary is related to extraction. For example, mining. For example, drilling oil. For example, fishing. This is primary industry. The other type of industry is secondary. This is related to manufacturing. For example, manufacturing automobiles, manufacturing electronics, etc. The third type of industry is tertiary. This is related to services. For example, in case of secondary industry, you manufacture vehicles, you manufacture buses, trains, etc. But based on those manufactured buses or trains or vehicles, you provide commute service. That commute service is known as transportation. So this is the tertiary or third kind of industry. So these are the three types of industry. And all these three types of industries have different potentials in becoming part of the Internet of Things, which means industrial IoT. Is that okay so far? So so this is the concept of industrial IoT within IoT. As you can see in this illustration, we have outer outline, we have a big rectangle that has Internet of Things. So Internet of Things is everything in it. Okay. Inside that rectangle, we have another smaller rectangle, blue color, which is industrial IoT. Inside that, we have another smaller, it's kind of a square, it's Industry 4.0. So this shows that Internet of Things is the umbrella. Inside Internet of Things or under the umbrella of Internet of Things, we have industrial IoT. Okay. Inside industrial IoT, we have another subset, which is known as Industry 4.0. So with this illustration, we can understand that IoT is the superset, industrial IoT is the subset of IoT, and Industry 4.0 is the subset of industrial IoT. Okay, so this means that from now on, when we are talking about industrial IoT, it means that we are also talking about Industry 4.0. So Industry 4.0 is the subset of industrial IoT. But then what is the difference between Industry 4.0 and industrial IoT? So the difference is that in case of Internet of Things, as you can see that anything can be part of the Internet, which means they can be industrial things, they can be non-industrial things as well. For example, as you can see here, your home appliances, your vehicles, your personal stuff, traffic management, your sensors, everything can be IoT. Okay. In case of industrial IoT, we are strictly talking about the industrial things. So we are talking about industrial sensors, factory-related sensors. We are talking about services, for example, catering service. We are talking about mining, etc. So in industrial IoT, the IoT things are the industrial things, not anything other than industrial stuff. Okay. So this is the concept of industrial IoT. Inside industrial IoT, we have Industry 4.0. In Industry 4.0, we are strictly talking about manufacturing industry. So as we learned here, there are three types of industries: primary, secondary, and tertiary. In case of secondary industry, we are talking about the manufacturing stuff. Okay, so this manufacturing stuff is this Industry 4.0. So when we talk about manufacturing only, then this is Industry 4.0. Manufacturing means manufacturing electronics, automobiles, etc. So as I said, from now on, we are talking about Industry IoT only. which means that we are talking about industry IoT plus industry 4.0. So up to here, I think we know that we have cloud, we have IoT, these are the two corners, but we have to integrate these two corners. Why do we have to integrate these two corners? The reason is that in case of cloud, as we learned that cloud has uh, practically unlimited resources. Cloud would provide us data, cloud would provide us storage, cloud would provide us computation, memory, all that stuff. Now, what is cloud going to do with all those resources? Cloud is going to wait for the data from different sources. And based on that data, cloud has a lot of power, processing power, memory, storage, all that stuff. So cloud would be building applications or services based on the data cloud receives from different sources. On the other hand, Internet of Things or IoT has various sensors, various objects. They are real life objects, they are dumb objects, they are static objects, they are mobile objects, it's everything in IoT. Most of those things have no processing capabilities. They have no resources as provided by a cloud. So those IoT objects or IoT things would be generating heterogeneous data, but they don't have resources to process the data. So those IoTs would be looking for a cloud-like entity to process data for them, to store data for them, or to create services based on the data they are generating. This is why cloud and IoT integration is very important. This is how both of these corners are connected. And the connection of cloud and IoT is usually referred to as Cloud of Things or COT for short. Okay. So when we talk about cloud and IoT integration, this integration is not possible without a middleware entity. Why? Because cloud is accessible over the internet and cloud is unaware of the underlying IoT devices. On the other hand, IoT devices are heterogeneous. It's a huge number of entities that can be part of IoT. And those entities would be on and off becoming part of IoT and exiting an IoT. So this means that we need a localized entity, an entity that is close to the IoT so that the entity can connect those IoT devices or those sensors or those objects and then make them accessible to the cloud. So this is why we need a middleware entity to combine both cloud and IoT, to integrate both cloud and IoT. That middleware entity can be of different type. This depends on the scenario that you have in IoT and cloud. For example, in a mobile scenario, the entity would be a particular type that can handle mobility. In a static scenario, the entity would be different, so on. Number of devices also affect this thing. So the middleware entity can be a cloudlet. The middleware entity can be a fog. Fog has two types. We'll learn it later in the presentation, so don't need to worry about this, the types of fog. The fog can be as a micro data center or a nano data center. This can be a femtocloud as well. Femtocloud means combination of your edge devices, for example, your smartphone. If you want to learn more about this thing, if you want to learn different middlewares, if you want to learn how different middlewares can be used, what kind of middleware I can use for any particular scenario, and all that stuff, for that, please refer to this publication, this paper. This paper contains all the details related to middlewares and how offloading can be performed. And also you can see this talk. You can search on Google this title and you'll find the talk on YouTube, or you have this URL. You can search through this URL as well and go over this talk. This talk is on offloading in fog and IoT. So you'll learn everything about the middleware entities and learn everything about how offloading can be performed, what are the reasons, and in what scenarios, what kind of offloading can be performed, etc. So far, we have learned what is cloud computing, we have learned what is Internet of Things, we have learned that both cloud and IoT have to be integrated, and we have learned that their integration is possible only through a middleware entity. We have also learned that there are different types of middleware entities, and based on our particular scenario, we'll choose the right middleware entity. The middlewares are usually accessible. They have two different layers. So either the middleware entity would be accessible at the next hop, which is known as zero hop, and this is known as technically, this is a Cisco term, this is known as mist layer. So the next top layer is your mist layer. At the bottom are your edge devices. These are your end users. These are your industrial IoT devices, or these are your IoT devices, etc. When they access a middleware next level, the next hop is the middleware, then this is known as mist layer. And if the middleware is accessible after one hop, so this is your first hop, this is the one hop. So next hop and first hop. So this is the fog layer. Fog can be in the form of smart gateway or micro data center, etc. And then over the core internet, you have your cloud. So this is multi-hop. This can be 3 hops, this can be 10 hops, this can be 20 hops. So this was the background. So let's see what is the role of fog computing. As this is the almost the end of this workshop, so I suppose that you already know about fog computing. But let's run through the basics of fog computing. Now, you know what is cloud computing? We learned it in the beginning. Cloud would provide you resources. What kind of resources? Like data, it would provide you computation, it would provide you memory, it would provide you storage, all these things. All these same things can be provided by a fog as well. Fog has the same resources as of a cloud. Then what is the difference between fog and cloud? The main difference is the location of fog. So cloud is accessible over the internet and cloud is multi-hop. Okay, it is accessible over the core network. In case of fog, it is localized, it's nearby. For example, it's within the building or it's within the city, not more than that. This is known as, so this is a localized cloud and this is known as fog. So the main difference is the location. The other difference is, since fog caters for a smaller number of users, so the scale of those resources is very small. Compared to a cloud, the resources that are provided by a fog, they are not practically infinite. They are limited resources. Generally, fog has 2 types. One is micro data center. In case of micro data center, you are talking about a few hundreds of customers. In case of nano data center, it's kind of a gateway which is always accessible, and that gateway has additional capability of performing computation or storing the data. So you're talking about a few tens of customers or so. So these are the 2 basic types of fog computing. If you want to know more about this, then please let me know, or we can go over some paper or something. But I assume that since this is the end of the workshop, so you know about fog computing already by now. And you can also go over this publication and learn what is fog computing versus cloud computing and how fog computing complements cloud computing. So what are the benefits fog computing will provide you when you integrate fog with cloud computing? Let's see what are the key components of industrial IoT. So components mean without these things, industrial IoT would not be complete or would not be possible. So this is the first and foremost thing that you need in an industrial IoT. Localization of wireless sensor networks and wireless sensor actuator networks. So in an industrial setting, as we learned that if it's a factory, if it's a smart factory, if it's an industry, then you have different types of sensors deployed in that industry. Okay, the sensors would be related to monitoring the environment, for example, CCTV cameras. They would be related to temperature, related to pressure, location, smoke, leakage, chemical reaction, humidity, etc. All this stuff. So you can assume that there would be hundreds of sensors deployed in an industrial setting. Those hundreds of sensors would be, some of them would be connected to each other, and eventually they would be connected to a middleware entity, for example, a fog. Okay, so those sensors have to be connected to that middleware entity to make them able to send the data, and then the middleware entity would be able to read the data. So the data has to be readable. So I am receiving data from, for example, 100 sensors. Does that data make sense to me or not? Those sensors are heterogeneous. One sensor is manufactured by one company, and that company is using different protocols. The other sensor is manufactured by another company using different protocols. So the data structure is different. I have to make that data readable to me. I have to make that data sensible to me. And for that, I need to localize those sensors. Localization means I have to make them present in that environment. Otherwise, they would be individual sensors not connected to me, not connected to my industry, not connected to my industrial IoT environment. Okay, so when we connect those sensors wirelessly, this is known as wireless sensor network or WSN. Okay, and when we talk about actuators, actuator mean this is an object, this is a device that can somehow move and control its environment. So when sensor is a stationary thing, sensor is a static thing. But in case of actuator, actuator can move as you can see in this picture. Actuator can move or control something. So this means that actuator's job is slightly different from sensor's job. So in case of actuator, you might be controlling the actuator through the internet because we are talking about industrial Internet of Things. So it means that the actuator is also part of the internet. And if it is part of the internet, then probably I'm controlling the actuator remotely. If I'm controlling the actuator remotely, it means that when I take an action, the actuator has to perform that action immediately. Otherwise, there can be a catastrophe. Otherwise, there can be a malfunction of an object or any device. So this means that I need reliable data, fast transmission. Not probably in the case of wireless sensor networks, but definitely in the case of wireless sensor actuator network. So this is the difference between wireless sensor network and actuator network. So in case of actuator, you need more reliable data and you need fast transmission. And in case of actuators plus sensors, energy consumption would be a big problem. So I need a middleware entity that can monitor the energy consumption of all my sensors. And if I need to put some sensors on sleep for some time, for example, I don't need the CCTV or video capturing of any particular place for some particular time, then I need to turn it off. Similarly, if I have different sensors and I don't need a particular sensor from hour 4 to, for example, 8 p.m., then I need to turn that sensor off or put that sensor on sleep. So to do all these things, I need a middleware entity. There is a fog. So this is how, as you can see that in case of industrial IoT, localization of sensors is very important. Okay, and to enable localization of sensors, we need a middleware entity, and one suitable entity is fog computing. I hope everything is so far clear. So I'll move to the second component. So this is the second component. This is virtual sensing and virtual sensor networking. So we just learned that there are heterogeneous, there are numerous types of sensors that are required in an industrial setting. In many scenarios, we have the same sensor that we need for different scenarios. For all those different scenarios, is it viable to have physical sensors deployed in the industrial setting? It would cost us too much, right? So if we have, for example, if we have 10 different scenarios for any particular sensor, for example, temperature sensor, does it make sense to have 10 different physical sensors to have in the industrial environment? 10 different physical sensors means you need physical power for those sensors. You need to physically purchase those sensors. You need to maintain those sensors and all that stuff. So this is quite expensive. What is the solution then? If you talk about industrial IoT, we are not talking about industry. We are talking about industrial IoT. So this is a future technology. So solution is to have virtualization technology in that case. Just like you use virtualization technology to virtualize your resources in fog computing and in cloud computing. I hope you have heard about virtual machines. In the same case, you have virtual sensors. What is virtual sensor? When you have a physical sensor and you softwareize your physical sensor, it means that you have a software copy of your physical sensor and you modify the software copy based on your requirements. This is known as virtual sensor, and this technology is known as virtual sensing. And when you connect different virtual sensors, this is known as virtual sensor networking or VSN. Okay. So this is the key concept of virtual sensing and virtual sensor networking. And an example is you need to monitor temperature for different scenarios. For example, monitor temperature before manufacturing, monitoring temperature during manufacturing, and post manufacturing. So instead of deploying 3 different physical sensors, you have one physical sensor and you make use of that physical sensor through software, through virtualization, and make copies of that sensor. In the same way, you can make copies of the same physical sensor for different settings. For example, in one room you have this physical sensor, in another room you need a different type of physical sensor. So you can do the same things. So just to recap, that right now we are talking about the key components of industrial IoT. Without these components, industrial IoT would be incomplete. The first component was localization of sensors, the second component of using virtual sensing technology, because otherwise industrial IoT would be too expensive. What is the next thing? The next thing is controlling and managing CPS. CPS stands for Cyber Physical System. So what is Cyber Physical System? We know what is IoT. We know what is industrial IoT. What is CPS, Cyber Physical System? Cyber Physical System deals with embedded systems and devices connected to the cyber world. Cyber world means related to information technology and internet. So when your embedded devices, your embedded systems, they are part of the internet, they are part of the cyber world. This is known as cyber physical system. Examples would be your actuators. Example would be your robotics, robot related stuff in the industry, conveyor belt. Another example is vehicles as well, because vehicles also have the embedded system and they are a device, okay? But in case of vehicles, we talk about the connection of vehicles over the internet as Internet of Vehicles or IoT. So in case of CPS, it means that we're generally talking about the industrial setting. CPS is a subset of Internet of Things. The difference between IoT and CPS, as I explained, is that in case of CPS, we are talking about embedded systems and devices. In case of IoT, we are talking about anything, Internet of Things, so anything. But in case of CPS, we are not talking about anything. We are strictly talking about embedded systems and devices. Okay. So why do we need CPS? Why do we need to manage and control CPS in industrial setting? We know that CPS means these embedded devices, these conveyor belts, these robots, these actuators in industrial setting. We need to control and manage them because we need to automate the process. If these devices are accessible over the internet, we can automate the process. We can control these things. We can control our industrial setting over the internet. What is the other benefit? The other benefit is that we can diagnose the problems beforehand. So instead of reactive measurements, we can do proactive measurements because we know that our devices are moving or performing jobs in a particular fashion, so we can analyze that. Also, we can perform better management and cost-effective reconfiguration of our industrial devices. In the same way, since these devices have become part of the internet, cyber world, it means that they are accessible over the internet. Since they are accessible over the internet, it means that we can create additional business models or business processes through controlling and managing CPS. So that's another important aspect of industrial IoT. Without this, industrial IoT would be incomplete. So these are the three main components. What is the next one? Okay, so we have a layered architecture of CPS as well. Let's go over it quickly. So at the bottom, we have the CPS nodes. These are your embedded devices. These are your machines. These are your actuators. These devices are connected using wireless technology. For example, Wi-Fi, for example, Zigbee, for example, 5G, for example, visible light communication or VLC. Visible light communication would be really handy in case of industrial setting because most of the industrial devices would be static. So you have a visible light directly beamed at a particular device, and hence the bandwidth would be much better and there would be no interruption. So that's a huge future potential and use case of visible light communication or VLC in terms of industrial IoT. One of the examples of visible light communication is Li-Fi, L-I-F-I, this one. So after the connection, you have an entity that can control these devices, that can read these devices, that can localize these devices. So what is that entity? That entity is a middleware entity. For example, a fog microdata center or anything like that. Once you have received the data through the middleware, then you would send the data to the cyber world. This is your cyber world. So what are you going to do with that data? What are you going to do with getting data from these devices here? You're going to perform data analytics, you're going to store the data, you're going to perform distributed storage, and you are going to create relationships between or among those entities. When you create relationships, this means that you're talking about semantics, you're talking about ontologies. So based on that, your data is more useful. Once you have these actions performed, then you're able to perform cognition on that data. Cognition means you're creating intelligent services. How would you do that? You would do that through machine learning and through deep learning. Once you have done that, you have a cyber world where you can access these entities, you can access them here. How do you do that? You do that based on human machine interaction. Okay? Once you have done this thing, this means that you can control your devices here. Once you're able to control these devices, it means that you can perform an action from here, and based on that action, these devices would be remotely controlled and they would perform their tasks, the required tasks. And in the same way, you can create business based on the access or connection of these devices. So this is how the CPS would work. Another important component of industrial IoT is industrial big data analytics. So up to here, I think we know that we have different sensors, we have sensor networks, we have different actuators, we have actuator networks, we have different cyber physical systems, we have virtual networks, we have everything. This means that we have heterogeneous data coming from numerous devices, thousands of devices. We have to make use of that data. That data is not useless. That data would give us control over the industrial setting. That data would give us means to create new services. And that data would give us means to integrate with other services within the IoT domain. So to do that, we need to perform data analytics. We receive data from every entity. We perform data analytics, and that is useful for different use cases. For example, for accounting, for quality assurance. If you don't do data analytics, you're not able to assure that the quality of your industrial process is good or not. You can do research and development. You can enhance your import and export, recycling, energy efficiency, fault detection and fault tolerance, deep learning, all that stuff, and many other things that you can do through big data analytics. And I think this code is worth sharing here. This is the truth about the data, and this is the future about the data that we are talking about in today's world. So, this is the last component of industrial IoT, another very important component, Web of Things for industry. So, what is Web of Things? We know what is Internet of Things. We know what is Industrial Internet of Things. We know what is cyber physical system. Then what is this new thing, Web of Things? Web of Things means when sensors and actuators are becoming part of the web service. So what are the key words here? Sensors and actuators, number one, and number two, web service. So in case of Internet of Things, we are just talking about connecting those things and then receiving the data from those things and then creating services based on that. Okay, this is Internet of Things. But in case of Web of Things, we are talking about sensors only, sensors and actuators. And we are saying that they're not just becoming part of the internet, but also they're becoming part of a web service. For example, a waste management company has different waste bins. Those waste bins are sensor equipped and they give real-time data or they give updates on the amount of waste a waste bin has. So at different locations you have waste bins and you're receiving the data from those waste bins. Who is receiving the data from those waste bins? The waste management company. In some countries, it's a private company. In other countries, it's a municipality. So municipality is receiving the data from all those different bins. Now we have another entity here. They are recyclers. The recyclers want to know what type of waste is coming up in this month or in this week, and in what quantity. For example, how much of plastic, how much of paper, how much of aluminum, etc. So what they do is they connect to the web service of the waste management company and receive data from those sensors or from those waste bins. So this is how connecting to a web service, connecting to sensors, create Web of Things. I hope it is understandable. So this Web of Things is another part of, or it's actually a refinement of IoT. So in industrial IoT, Web of Things will be really important. I'll explain you one of the examples of this smart waste management in the slide next. So let's have a short pod break. Okay, so fog enabled industrial IoT. So far, we have learned the background of this presentation. We have learned the basics of fog computing. By now, we know what are the key components of industrial IoT. We need to know what does fog do in case of industrial IoT. What do we get when we include fog computing in industrial setting? Let's see that. So I think so far you have an idea that how and in what way fog computing is important in industrial IoT. What would fog do, in your opinion? So these are the key things. Number one, offloading. You know that there are different sensors. You know that there are machines, there are devices. Those machines and devices cannot perform computation. So they need to offload things, they need to offload computation. They are giving data to fog and they're asking fog that please create a service based on this. Please do this thing for me. Please analyze the temperature setting. Please let me know if this temperature plus this humidity means something. For example, I'm getting reading from a leakage sensor, gas leakage, for example, and I'm getting reading from a temperature sensor, a high temperature and a gas leakage. This means that I have to analyze this thing and beforehand proactively see that if a fire is going to happen. So based on that, if an accident is going to happen, I can determine this thing beforehand. So this is only possible when you offload your data to a resource-rich entity. So this offloading is one key use case of fog computing in case of industrial IoT. The other one is energy consumption. Monitor the energy consumption of your sensor networks, your devices, so that you can manage this thing more efficiently and consume less energy. And also find out other sources of energy. For example, solar energy, thermal energy, body heat, etc. All that stuff. Also, you have sensors and devices in your industry from different manufacturers. As I said before, that they are created by different vendors with different protocols, different data frequency, different settings. So you need to be able to interoperate all those sensors and devices within an industrial IoT. This interoperability should be seamless. How is it possible? It is possible only through fog computing. So fog would enable the interoperability through application programming interface and other protocol translation stuff. Another benefit of fog computing in industrial IoT is bridging short-range protocols. So I have a device that can send data to a certain extent, to a certain range. I have to extend that range because I have a bigger, larger industrial setting. How is it possible? It's possible through a nano data center, a fog gateway type of thing that can receive the data and then relay the data to the next hop. The other important thing is security. So I think security is one of the major issues, one of the major challenges industrial IoT would have. We're going to talk about it in the research challenges section, but for now, I think this is very important, and I guess you have the idea about it that since we are talking about making industrial things available over the internet, it means that they are prone to attack. External entities can attack these industrial settings, these industrial environments, these industrial sensors, the industrial data, and all that stuff. So we have to make the data secure. We learned in the beginning that cloud is accessible over the internet. It means that we cannot simply receive the data from sensors or from an industrial environment and send it over the core network to the cloud, to the public network. It's not possible. We have to first secure the data and make the data privacy available. So how is it possible? There are two possibilities. One possibility is cryptography. But in several settings, in several scenarios, cryptography won't be a viable solution. Why? Because cryptography would take more processing and more time to do. So in that case, the problem would be that, for example, if you're talking about an actuator needs a fast response. So cryptography won't be a viable solution. The other solution would be that you have publish-subscribe approach. In publish-subscribe approach, you have your publishers and you have your subscribers. So you're sending the data only to your subscribers, which means that you know who is receiving the data. You're not broadcasting the data. So this is another important thing. The security and privacy feature is another important thing that fog computing would provide you in industrial IoT. And without fog computing, this thing won't be possible. This is how fog computing would look like in industrial settings. So you have your all different industries. This is one kind of industry. This is another kind of industry, transportation. This is third kind, fourth kind. So you have all your industrial settings. You have all your different industrial IoTs. They are connected to different types of fog nodes, and those fog nodes will be providing different services. This depends on your environment. For example, storing the data, for example, data analytics, providing connectivity, interoperability, all that stuff, virtual resources, virtual sensing, etc. And then fog would be able to send the data, the secured or enhanced data or refined data or structured data over the internet to web services. So this can be your CPS, this can be your any general web service, this can be your cloud, etc. So this is how fog would be lying in an industrial setting. Let's talk about those industries now where fog computing would be playing its role. The first and foremost is your primary industry, which is mining. So in case of mining, mining contains a lot of risks. Mining is adventurous. So if you don't have enough sensors, if you don't have enough analytics of the data that you receive from sensors, then you're not going to be able to get the technology on board that you need for an industrial IoT. So in case of mining, you have to deploy your sensors, you have to deploy your devices, and then you need a localized processing. You cannot send the data over the internet to a cloud. You need a localized fog. The fog is going to receive the data from those sensors, for example, a pressure sensor, for example, a vibration sensor. Based on these sensors, you can tell that a rock sliding is going to happen and how much is going to be the impact, etc. All these things. Similarly, a gas leakage or leakage of any liquid or anything hazardous, chemicals, all that stuff. So you can determine these things based on your data analytics. And data is coming from all your different sensors. And that data can be made readable or can be made meaningful only through fog computing. So this is how in mining industry you can use fog computing and you can enhance your mining industry. So in that way you can cut your costs, you can cut the accidents and all that stuff, and better energy efficiency, accuracy, and management of your services and your resources would be made possible if you use fog computing in a mining setting, mining industry. So another industry is smart grid and power industry. So what is smart grid? So smart grid and the regular grid are different in a way that in case of smart grid, you have two-way communication between your provider and your user. In case of your regular industry, without smart grid, the regular grid is they're providing you the power resource and you're receiving the resource. That's it. It's just one way. You're just receiving the electricity and you're paying the bills for it. It's one way. In case of smart grid, you're not just receiving the power, you're not just receiving the resource, but you're also providing the feedback. How are you providing the feedback? You're doing that through advanced metering infrastructure or AMI. Okay. What is AMI? AMI is composed of advanced sensors, meters, communication infrastructure. So communication infrastructure means you're probably taking on board your telecommunication industry. So right now, your power industry is completely dependent on a power resource, power company, a company that provides you electricity. That's it. No other company is involved in that case. But in case of smart grid, telecommunication industry would be involved as well. So this means that you have different entities that are taking part or you're playing their role. Then you need to compute those the data coming from those resources or from those entities. And then you create applications and you manage the data. So this is the part of AMI, Advanced Metering Infrastructure. And Advanced Metering Infrastructure, or AMI, is part of your smart grid. What else? So AMI would be able to get the data from you and send the data in real time to your service provider. So what's the benefit in that? The benefit is that the service provider is going to give you feedback and suggestions based on your usage, based on your appliances, based on the current time of the use. For example, if the evening time is more expensive to use a particular appliance, your service provider can be able to tell you that if you use your particular appliance, for example, your washing machine in the morning, because it would consume more electricity, then it's much better for you. And use your another appliance in the evening, for example, because it's cheaper in the evening. In the same way, what you can do is You can uh, you can get the data from all those sensors, you can get the data from all those meters, from all those devices, and then perform data management based on that. So the consumer premises have different data communication requirements. For example, a smart home will be generating less data as compared to a smart building. A smart building would be generating less data as compared to a smart building. So based on your different environments, based on your different industrial settings, your smart grid users, based on that you have different type of data usages. So why is it important? It is important because you need to determine your correct data communication and data flow management techniques based on your users, your type of users. Okay. So this means that you have to build flow management and you have to perform tasks related to flow management. How is it possible? It is possible through software defined network or SDN and network function virtualization. Do you think SDN and NFV would be possible without fog computing? No, it's not. So this is why you need fog computing in smart grid industry and power industry. Let's run through the key differences so that you have a clear idea of why all this thing is important that I explained here. So this is the key difference between your regular grid, traditional one, or your smart grid. So in the traditional grid, you have power resources and they are limited resources. Okay, so your power is coming from one, two, or three different resources. For example, tidal resource, for example, hydel power, nuclear power, etc. In case of smart grid, you have multitude of resources. So the power would be coming from private people as well. For example, at your home, you have enough surface to receive sunlight and you have installed solar panels. So you receive energy from solar panel and then you distribute that energy to different users. So this is how smart grid would be different in case of production. Then in case of market, so you have all, in case of traditional grid, you have all the resources gathering at one point. In case of smart grid, you have individual customers. So they would be receiving the resource from different other places. So this means that this is distributed as the role of fog computing is, as you can see. Similarly, you have smaller pipelines, you have smaller means to distribute the energy. And as I mentioned before, that compared to traditional grid, your smart grid has two-way communication. At the end, the user would be participating as well. Instead of just receiving, user is giving the feedback and receiving the feedback and suggestion from the service provider, and also becoming part of the system. So how would fog lie within this smart grid scenario? This is how your fog would be. So your fog is connected to different smart grid industries. For example, this is electric vehicle. You have smart factory. You have subways, and you have smart meters at home, smart home, etc. All that stuff. Sorry. So you're getting the data from them. The data frequency is different. Data communication requirement is different. Based on your data communication requirement, based on your frequency, you're creating flows of data. When you create flows of data, it means that you have to create a software defined networking enabled fog. And then that fog can send the data to the smart grid and then better management of resources can be provided. This is one example of why this kind of a technology is important in industrial setting, especially in case of industrial IoT. As you can see here, that Google is working on a project known as DeepMind, and based on that, they have claimed that if they perform machine learning related tasks, then they can enhance their capacity of receiving the energy or production of the energy by up to 20%. So this is possible through machine learning. Machine learning would be possible if you have deployed fog computing technology within your smart grid setting. So this is how, as you can assess, it is important to have fog computing like resource entity. Another important industry is transportation. Transportation means you have buses, you have trains, you have private vehicles, all that stuff. These things can be made part of the internet and you can create smart services based on that. So when you create smart services based on your vehicles, this is known as intelligent transportation system or ITS for short. So how would that be possible using fog computing? It's possible when you have roadside unit that is equipped with fog computing. So I'll just quickly go over this thing because we are running. Uh, we don't have, I think, enough time for that. So this is one example: driver behavior monitoring and assistance. So monitoring the behavior of the driver through sensors would be very important. That is possible through fog computing. Why is it important? Because you can assist the driver, you can monitor if the driver's behavior is ethical or not, if the driver behavior is good for the overall commute system or not, overall transportation, and all that stuff. You can also assist the driver based on the weather condition and road condition as well. For example, snow, rain, light conditions, and all that stuff. You can go over this. You can go over the details in this paper if you're interested. This paper has all the details related to the driver behavior management. Why sensor networking, why fog computing is important within the transportation system? This is one of the reasons. World Health Organization suggests this thing. So if you're driving above 50 km per hour, the risk of dying is 20%. If it is above 80%, the risk of dying is 60%. So it's a huge difference. And how would you determine this thing? You would be able to determine this thing if you offload your driver. So your driver don't have to process everything. Rather, you have sensors within your vehicle, and the sensors are telling the driver that in this particular condition, you have to adapt your speed, you have to adapt your driving behavior in this way, etc. This is an example that you have this vehicle. For example, this is a cargo vehicle. So this vehicle has three different categories of sensors. You have driver sensors. These sensors are monitoring the driver. For example, driver's vital signs, driver blood pressure, blood glucose, heart rate, etc. And you have environment sensors. For example, the road condition, the weather condition, the lighting, etc. Then you have vehicle sensors. For example, seat belt sensor, the driver compartment sensors to monitor the condition of that compartment, and also the cargo sensors. So if you have a cargo vehicle and you have goods transported from one location to another, then based on the inside temperature, based on the requirement of the goods, and compared to the outer environment, you can have those sensors. So based on this, you can create an intelligent transportation system. So this is possible through fog computing. And in this particular case, you have two types of fog nodes. One is your roadside fog unit, so roadside fog, and the other one is your vehicular fog, which is inside the vehicle. This one is in the environment, and this one is within the vehicle. For short, we call it VFog. This can be a scenario or a combination of different scenarios that fog computing would provide you in case of transportation. So what is this? A vehicle has crashed, and the information related to this vehicle can be communicated to a nearby fog. This can be done directly or through nearby passing vehicles. Okay, this is possible through Internet of Vehicles. So this information goes to this fog, and this fog will request for an emergency vehicle. An ambulance is coming, so this vehicle doesn't need to call for ambulance. Rather, your fog would be able to determine whether a crash has happened and there is no movement, so I need to call an ambulance. And based on your road conditions, your speed limit would be monitored and managed in real time. And then based on the approaching emergency vehicle, you can control your traffic light. So this is known as smart traffic light. So this traffic light would be turned on as the emergency vehicle approaches the signal or this intersection. So every other traffic would be halted, and this vehicle can move and reach this place. These are the different scenarios, different examples of how fog computing can enable smart transportation or intelligent transportation system. Another important industry is waste management industry. Timely management of the waste is very important. Why? Because it would prevent creation of different diseases. And what else? We can do recycling in a better way. What else? We can do waste to energy in a much better way. So, I think this is a very important statistic. So we have food wastage with this level. Okay. So we have 1/3 of the food that is produced overall and goes in waste. So as you can see here, food wastage in rich countries is almost equal to food produced in sub-Saharan Africa. So in one part of the world, the total food produced is almost equal to the food wasted is in another part of the world. So this means that this is a huge number. This means that a lot of people are deprived only because we are not using the right technology. Let's go into further details of what kind of food is wasted. So 45% of your fruits and vegetables are going in waste in general overall in the world. 45%. This means that almost half of your fruits and vegetables are going in waste. Why? Because we are not using the right technology. We are not determining how to manage the waste beforehand because we are not using smart waste management techniques. 35% of your seafood, 30% of your cereal, 20% of your dairy products, all that stuff. This is a huge number. Why? Because the regular waste management process in most of the countries is like this. You collect the waste, you transport it, you segregate the waste. For example, this is plastic, this is aluminum, this is organic waste, etc. Then you perform the recycling related stuff, and then the final disposal of the waste. For example, through landfill or by burning the waste. What is the solution? The solution would be to have the industrial IoT technology. These are the key issues or challenges in the current system, as we have already, I think, guessed by now. So let's have smart waste management. What is that? You have a waste bin, and waste bin is equipped with sensor. Through this sensor, the waste bin would be able to tell the quantity of the waste in that bin. How much is the waste? You don't have to open the lid to see how much the waste is. This sensor can send the data through a nearby router to the waste management company, and the waste management company would be able to determine how much of the waste of any particular type at any particular location is, and when do we have to schedule a visit to go there and then pick up the waste. And similarly, in the same way, the recycling companies can connect to this system, and then they can assess that, okay, in this month we are getting this much of paper, we are getting this much of aluminum, so we don't need to import anything, or we need to import X amount of paper from the outside because we are getting this amount of Y amount of paper from the inside. So we can do all this stuff through smart waste management. So we have segregated waste bin, organic, paper, plastic, and we have sensor equipped waste bins. So how do we do that? We do that using fog computing. So you have fog that is receiving the data from all those sensors, from all the waste bins within your city. Based on that, the data is sent to the waste collectors. The waste collectors can optimize their route. We don't need to go to this part because the waste is still not enough there. So we need to go to this waste bin, this location, this part of the city, this part of the city, etc. So this would cut the cost of fuel, this would cut the cost of traffic, this would cut the cost of human resource. This is what you can achieve through smart waste management or fog-based smart waste management. You can go over further details in this paper. And more details, so this is just a general thing. More details on different industries can be seen here in this paper. So I've talked about a few industries. There are many other industries as well. So you can go over those industries in this paper. We have an evaluation, a generic evaluation of fog computing in an industrial setting. So how would fog perform? We are talking about fog computing a lot. We don't know if fog is viable or not. Let's see if it is. We have a cloud sim based evaluation, and this evaluation shows that if you have 10 billions of instructions to 1000 billions of instructions of a task. So the reason why we are using billions of instructions is because we have been talking about machine learning. We have been talking about data analytics. So usually data analytics and deep learning related tasks would be based on a few billions of instructions. That is why we are using billions of instructions as the unit of assessing fog computing's performance here in this result. So from 10 to 1000 BI, this is the performance of fog. If you want to enhance the performance, you have to enhance the capabilities of the fog. Now it comes with a cost. Let's see what is that. As you can see in this result, the first one, so this gray area, this is the processing cost. The yellow area is millions of instructions per second. This means that this is your processing capability. In this first case, in this first instance, the MIPS are 250. So with 250 MIPS capability, if you have a 40 MB, the reason why it's 40 MB is because we're talking about the data size right now. We're not talking about the business instructions. We don't know how much processing we need, but we're just talking about the size of the data that we're transporting from one location to another location. Since we're talking about the communication right now, that is why the unit is megabyte rather than billions of instructions, because we wanted to keep it generic. So with 250 MIPS with 40 MB of data, the processing cost is 0.002375 per hour. Okay, and the processing and the delay is 240 milliseconds. Okay, in one setting, this 240 millisecond would be acceptable, but in another setting, this won't be acceptable. Let's see what is the difference in that case. Let's go to this third case. This was the first one that we talked. Let's go to the third one. Now, in the third case, as compared to this 250 MIPS or millions of instructions per second, we have increased the capability of our fog. Now, fog is 5200 MIPS. So fog's capability is increased. Previously, the delay was 240 milliseconds. In this case, the delay is, how much is that? 23 milliseconds. A huge difference, right? It's a huge difference. 10 times less than the previous case. And what is the other difference? The other difference is that the cost was previously 0.002375 per hour dollars. In this case, the cost has increased 0.475, as you can see here. So this is the processing delay. The delay was here, and the delay came down to this point. This was the task length. The task length was increased here. This was the processing cost, the gray one. As you can see here, this gray part is so small, but this gray part is huge. So it's a trade-off. If you enhance the capabilities of your fog, you can get a better performance, but this would come at a cost. If you can bear that cost, then obviously you would do this thing otherwise. So overall, it's a trade-off between your processing cost, your processing delay, and your processing capacity. The last part of this presentation is your research challenges. Let's run through them quickly. So the first and foremost challenge, so far we know what is industrial IoT, we know the role of fog computing in industrial IoT. So I guess we are impressed that, okay, industrial IoT is really good, industrial IoT is very important, we need industrial IoT, we have so many new things coming up through industrial IoT. So yes, we are impressed, yes, we need industrial IoT in the future, but are there any challenges that we have to deal with in the future if we talk about industrial IoT? Yes, there are. The first and foremost challenge would be energy consumption and management. In industrial IoT, several devices would be part of the IoT. Sensors would be part of the IoT. Machines, embedded devices, they will be part of that. So we need to manage their energy consumption. This would be a big problem. Okay, more and more devices coming in, more and more energy consumption, more and better energy monitoring solutions would be required, and energy management solution would be required. So one of the key things would be to find alternate energy resources, for example, solar energy, etc., or rechargeable energy, things like that. In the same way, we need to be able to determine that if there is a certain scenario that might be better to run in a particular time. For example, one type of industry would be run at night, another type of industry would be done in the morning, during the daytime, etc. So you have to manage these things. And this is the key challenge actually. This is not an easy thing. This depends on every country. This depends on the different industries in a particular country, their seasons, their climate, and their resources as well. Other important thing, as we have discussed this thing before as well, that you have devices and entities coming in from different sources. Many of them would be not interoperable with each other. So you have to make them interoperable. And this interoperability would be very important in the case where you have actuators and robots. Why? Because you need fast response. So you need a seamless and high performance interoperability of devices. So it's not just interoperability, it's seamless and it's also high performance also. The other thing is service level agreement. We are talking about industrial IoT. This means that SLA matching, SLA monitoring, and the violation of SLA would be an important thing, because we are getting data from different entities, from different sensors, We learned that in case of Web of Things, the sensors are becoming part of a web service. This means that the web service is a third party entity. So we need to negotiate the service level agreement with them. So one entity had a service level agreement with the user. Now we are involving another entity. This means that we have to renegotiate the service level agreement. So this is going to be a big problem in the future when we have industrial IoT. So this on its own is a different research topic. SLAs have different types. Okay, let's talk about all those different types quickly. SLAs, one type is, different attributes. So one attribute of SLA is that it has to be meaningful. This means that all the involved parties have to understand this SLA. This SLA has to make sense to all those parties. I have customers, I have an SLA with them, and right now I'm involving another company with that. I'm involving another web service in my overall service scenario. Then in that case, my SLA should be meaningful to the new company as well, to the new web service as well, measurable, so that I can compare my SLA. I told my customer that I'll give you this service based on this unit and at this price. Now I'm involving another entity. That entity has a different unit. For example, one entity was using a different scale, the other entity was using another scale. Now I have to make it measurable as well, comparable as well. The other attribute is controllable. So the service satisfaction could be modified and achieved based on the requirements. So your service satisfaction would be was different in the previous case, and right now it's different. I'll give you a shallow example of that just for comprehension. That, for example, a service provider asks you to rate their service from 0 to 5. So the best service would be 5, the worst service would be 0. Another service provider asks you to rate their service from 0 to 10. So how would you compare 0 to 10 to 0 to 5? So this is how this has to be controllable. Then affordable as well. So it has to be cost effective. When you're involving new entity, it should not get more expensive. So this is another big challenge in case of industrial IoT. And then acceptable, you don't have to dictate your SLA. You have to negotiate this with your customers. You have to negotiate this with all the involved entities. Security and privacy of the data. We learned this before as well, that we are talking about sending the data over the internet. The data is becoming part of the internet. The machines are becoming part of the internet. So the data has to be secured first. More and more connectivity, more and more devices means that the data is more vulnerable to attacks. And above all, you need the security of your workers. So based on your sensor technology, you have to determine this thing, that if an action is performed, is it safe for your workers as well or not? This is possible through sensor networking and industrial IoT, but you have to perform these measures. This is a challenge as well. If we have sensors and devices, we'll also have, just like autonomous vehicles, we'll also have autonomous vehicles in industrial setting as well. So if we have autonomous vehicles that are doing things on their own, then we need to make sure that it's safe for the workers or the people around that place as well. We have data from all the resources. We have to make sense of the data. How is that possible? It's possible once we are able to make relationship between the data coming from different devices, different entities. Once we are able to do that, we can create different complexities, and then we can create intelligence on top of that. This would create semantics and context-aware service provision. We should be able to have better fault detection and reconfiguration. If our setting is not able, if the industrial IoT is not able to do better fault detection and self-reconfiguration, automatically reconfigure itself rather than waiting for someone to come in and then manually perform troubleshooting tasks. So another important feature in this would be that if a sensor or if a device is not working, then that device or sensor should be put on sleep so that the other sensors are not disturbed, because one sensor's output might be input of another sensor. User friendliness. In an industrial setting, you'll have different users. Several of them won't be educated enough, or they won't be aware of the technology. So how do you make this technology more acceptable to them? You have to make it more seamless to them. You have to make it more fluent to them. You have to make it more user friendly to them. This is another important and key challenge. It's not easy. When you're talking about industrial IoT, user friendliness would be a key issue because the users are unpredictable. The users are very diverse. They are not all educated users. So this is the conclusion of this presentation. Uh, we have resourceful things. We have advancement in different technologies. We are talking about IoT, so we can go towards industrial IoT very easily. But then there is a trade-off. We have all these challenges that we have discussed. It's a trade-off. You have to achieve one thing to compromise on another. You have to convert your opportunities. You have to convert these challenges or these shortcomings into opportunities if you properly analyze these challenges and do your research on this. So this is how this industrial IoT can be achieved. And this floor is now yours to ask any questions if you have any.